Walk into almost any industrial machine shop, and you will see high-volume flood cooling treated as the undisputed baseline for CNC machining. CNC, or Computer Numerical Control Machining, is the automated process of using pre-programmed software to dictate the exact movement of cutting tools. To keep those tools from overheating, the standard procedure is to drench the entire operation in a heavy, continuous stream of fluid. This practice is failing the aerospace sector. When applied to high-performance aluminum alloys, this heavy fluid actively degrades the structural integrity of the metal. This occurs because of a common industry assumption, the belief that applying a greater volume of fluid mathematically guarantees better heat management and longer tool life. The physics of bulk fluid application contradicts that logic. Pouring hundreds of gallons of coolant over a high-speed cutting zone is a chaotic process. It induces extreme, localized thermal shock and hydraulic stress rather than providing uniform cooling. Major manufacturers have recognized the risks. Companies like Boeing, Lockheed Martin, and Airbus are actively removing traditional flood cooling systems from their aluminum milling lines. Flood cooling treats temperature management as a brute force bulk removal problem. Modern manufacturing requires strict thermodynamic stability, which a chaotic liquid stream cannot provide. In aerospace, manufacturers frequently hog out up to 95% of a solid aluminum billet to carve out single, thin-walled fuselage sections. A billet is a solid, semi-finished length of metal that serves as the raw material for machining. Removing that much metal requires spindle speeds exceeding 20,000 RPM. This friction generates intense, localized heat directly at the cutting zone. The F-35 Lightning II bulkhead relies on this process. The F-35 is a supersonic, multi-role stealth fighter developed for global defense fleets. It uses monolithic parts, where a single aluminum piece replaces hundreds of individual fasteners and ribs. The financial risk attached to these parts is severe. A single stress fracture or tool breakage caused by improper cooling can force an inspector to scrap a part worth over $100,000. At this scale, fluid application is the primary vector for catastrophic structural risk. The liquid hits the friction zone intermittently, causing rapid temperature swings. Aluminum has a high coefficient of thermal expansion. This rapid cycle of expansion and contraction physically tears at the material lattice, inducing microcracking across the aluminum and fracturing the carbide cutting tool. This compounds on a macro scale through the puddling effect, where cutting fluid accumulates unevenly in the recessed pockets of a complex part. The Sikorsky CH-53K relies on a massive aluminum gearbox housing, vulnerable to this phenomenon. The CH-53K is a heavy-lift cargo helicopter used for transporting vehicles and supplies. Fluid pools in specific cavities, while other sections remain dry, creating a massive thermal gradient across the single piece of metal. The flooded, cold sections contract, while the dry, hot sections expand. This locks residual tensile stresses into the metal. The moment the clamps release the part, those stresses cause the thin walls to warp or potato chip out of tolerance. This uneven cooling permanently misaligns critical features like bearing bores. The bulk cooling method is the direct cause of the precision failure. In deep cavity milling, high-volume fluid becomes a physical mechanical obstacle. This causes what is known as hydraulic hammer effect. The hydraulic hammer effect occurs when hundreds of gallons of trapped fluid act as a solid mass, causing the high-speed tool to violently deflect as it strikes the liquid. In the machining of airframe ribs for the Bell V-280 Valor, this fluid-induced chatter leaves surface waves along the metal. The V-280 is a tilt-rotor aircraft that combines vertical lift with fixed-wing speed. At 20,000 RPM, centrifugal force throws the heavy fluid away from the cutter. The surrounding part is soaked, but the actual cutting edge remains completely dry. This leads to built-up edge.
Built-up edge, or BUE, is a condition where hot, gummy aluminum physically pressure welds itself directly onto the dry carbide tool. During the milling of Embraer E-Jet wing ribs, trapped fluid drags unevacuated aluminum chips back into the path of the degraded cutter. Embraer is a global aerospace manufacturer specializing in regional, business, and military aircraft. The tool drags those trapped chips across the surface, creating deep slug marks. These represent dangerous crack initiation sites that require labor-intensive manual polishing to fix. In high-speed, deep-cavity environments, flood coolant creates the friction and vibration it was originally designed to prevent. Aerospace alloys like 2024 aluminum contain high amounts of copper, making them highly reactive. Water-based coolant emulsions sit in massive open sumps where they lose their pH balance and become acidic over time. When this acidic coolant is trapped, it triggers galvanic corrosion. Galvanic corrosion is an electrochemical process where one metal corrodes when in electrical contact with another, in the presence of an electrolyte, in this case, the degraded coolant between the aluminum and the steel tool holder. In the production of integral panels for the Comac C919, acidic fluid trapped in blind holes caused deep, permanent pitting known as white rust. Comac, or the Commercial Aircraft Corporation of China, is a state-owned aerospace manufacturer focused on large passenger jets. This chemical instability degrades subsequent protective coatings like anodizing, causing total part rejection. In the automotive sector, cycle time and absolute part cleanliness are the primary manufacturing constraints. High-speed machining of large aluminum engine blocks often results in thermal expansion ghosting. Thermal expansion ghosting occurs when a metal part is machined while artificially chilled, causing its dimensions to drift once it returns to room temperature. If the finishing pass occurs while the engine block is drenched in cold fluid, the cylinder bores will warp out of circularity as the metal stabilizes. For Tesla's large, single-piece gigapress components, flood oil seeps into the porous cast aluminum. This contamination weakens downstream adhesive bonding and welding procedures. Bulk fluid application is incompatible with the precision geometry and extreme cleanliness required in modern high-volume manufacturing. Aerospace manufacturers are transitioning to near-dry machining, specifically relying on minimum quantity lubrication. Minimum quantity lubrication, or MQL, applies microscopic atomized oil droplets via a high-pressure airstream, directly through the center of the spinning tool. An atomized spray is a fine mist of liquid particles suspended in a gas. Instead of using bulk liquid to quench heat after it has been generated, MQL relies on precise lubrication to prevent friction heat from ever occurring. This chart compares temperature profiles. The flood cooling line is volatile, while MQL is perfectly stable, eliminating thermal microcracking. Mechanically, the high-pressure air blast instantly clears chips from deep pockets, preventing recutting. For high-end applications, Lockheed Martin uses cryogenic cooling with liquid nitrogen to maintain dead-constant metal temperatures. MQL enables the specific thermodynamic control required for stable, high-speed aluminum machining. Traditional water-based coolant is cheap to purchase, while MQL hardware requires an upfront capital investment. This chart breaks down the total cost of ownership. While flood coolant has a low purchase price, hidden maintenance and disposal costs dominate. Because MQL uses 99% less fluid, it eliminates the massive overhead of hazardous waste disposal. By eliminating thermal microcracking and built-up edge, MQL also extends the lifespan of expensive carbide cutters by up to 30. Furthermore, eliminating thermal warping saves tens of thousands of dollars on monolithic bulkheads that would otherwise be scrapped. When factoring in these production metrics, aerospace shops spending $23,000 on MQL integration achieve a complete financial payback in just 10 months. In the high-stakes world of aerospace aluminum, bulk fluid is an unpredictable liability. Precision lubricity provides the mathematical and physical control required for modern manufacturing.